Time and while. We previously learned how for loops can iterate through a list of elements, a string, or a file. Since we always know how long those values are, we can iterate safely in these forms of finite in an iteration. But what about times when we have to loop an arbitrary number of times? For example, if we need to repeatedly ask the user to enter input until the user successfully enters a number and not something invalid. For this, programmers have the while loop, which is a more powerful and therefore more dangerous form of iteration. It's sort of like an if statement, except instead of continuing on to the rest of the program, while the condition is true, the body will keep repeatedly executing. Anything that a for loop can do, a while loop can do too. However, a while loop can do some things that a for loop cannot easily do. Be careful though, the programmer must be very careful to avoid causing an infinite loop and letting the program run forever. Like for loops, we introduce some patterns for while loops that can help guide your coding. However, these patterns are much looser than the patterns we cover with for loops and are less generalizable. You can think of them as more like examples or loose guidelines at best. In general, you should try to think first if a given problem can be solved with a for loop before you try to jump to a while loop. You would not immediately leap to a chainsaw when a pair of scissors would do. But of course, sometimes you need a bit of extra chopping power, and a chainsaw becomes needed. In the same way, when you need a while loop, nothing else will suffice. These patterns can help you see opportunities for using this interesting control structure. How fast is your program? That is the question that we try to answer by using time complexity. The second half of this chapter introduces a critical idea about measuring how long a program takes, beyond our previous criteria of being correct and easy to understand. 3 different ways of measuring the length of a program are covered, including the number of lines, the time the program takes according to a watch, and an estimation approach called the RAM model of computation. We only really scratched the surface of the idea of time complexity, but this lays the foundation for a lot of important concepts later on. A substantial section of this chapter is dedicated to 2 specific problems: sorting and searching. These 2 problems have been seriously studied for many years in computer science and are very well understood. Furthermore, they have interesting properties that make them very educational for those just starting off. Searching is a problem we have seen before, where we are trying to find an element in a list. Previously, we used an iterative search algorithm to check each element. However, in the worst case, that might require as many checks as there are elements in the list. A massive improvement can be found by using binary search, which repeatedly divides the search space in half, achieving logarithmic time complexity. In order to use binary search, however, the list must already be sorted. Sorting a list means putting the elements in order. There are many algorithms for sorting a list, although we will only look at a few of them. You can expect to revisit searching and sorting many more times in the future.